All right. Starting from this video, we'll cover chapter 16, which is about vector calculus. And then this is going to be the last chapter we cover in this course. And then in this chapter, we're going to learn two more kinds of integration, two more different kinds of integration. First one of them is called line integral, and then the other one is called surface integral. But actually, each one of them has two different kinds of integrations. After all, there are four different kinds of integrations, two different kinds of line integral and two different kinds of surface integrals. In total, there are four different kinds of integration. All right. And then, but in this video, we'll cover section 16.1. That is more like a preparation for what we're going to do for those integrals. And the stuff we're going to cover is a vector field. Okay, and then let's remember in calculus 1 or 2, basically main objective study in calculus 1 or 2 is a function of a single variable, y is equal to f of x. And then from more sophisticated point of view, function is viewed as like an input-output system. And then so f is a function, and then the input space is R, the set of real numbers, and the output is also a set of real number. So this is input, and this is output, or output space if you like. And then for this reason, the value of the function, namely the output, for each input real number, we get an output, but output is a real number, namely the value of the function is just a real number, namely it's a scalar. So for that reason, this kind of function is called a scalar valued function. Scalar valued function. Then now, in calculus 3, so far, we have seen a function like r of t that's a space curve. Well, actually, not space curve, okay, plane curve, f of t, g of t. So that's a curve. Geometrically, that's a curve in R2. It's called the plane curve. And also, more importantly, we have covered space curve, f of t, g of t, and h of t. And then this is a curve in R3. R3. And then from this point of view, those two can be written as this. So first one of those here is also a function where the input is just one real number. So input space is the set of real numbers. And then the output is a vector in R2. And the second one is like this. The input is the set of real numbers. And the output is the set of vectors in R3. So the output is, if you identify each vector as a point in R3, we may write this function like this way. And then for this reason, the output is a vector. Okay, well, we identify each point with the corresponding position vector. So output is a vector. So for that reason, the value of the function is a vector. So for this reason, we say this is a vector valued function. Okay, then now also we have seen function like g is equal to f of xy, or with three variables, w is equal to f of xyz. And then those two can be written as like this, as an input-output system. For this, input is pair of real numbers, so it's R2. And for this, the next one, the input is R3, and the output is a real number. So for both of those, the output is just a real number. For example, for this case, for each given pair of xy's, xy is in R2 input, and we get as an output, we get just real number. And similarly for this, so therefore those two are, so to speak, scalar valued function. Because output is just one number, scalar valued function. Okay, then now we can generalize this as follows. Here's a definition. A function, namely it's an input-output system, where the input space is R2, and the output is also R2. So from R2 to R2. Or the input is R3, and then output is also R3. Such function is called a vector field. And then a vector field produces as an output a vector, right? It's R2 or R3. So a vector field is a vector valued function. It's an example of vector valued function. Vector field is a vector valued function. All right. For example, vector field. Oh, by the way, because vector field is a vector valued function, we use like a symbol like this, vector symbol. Well, some people use F and the arrow on the top, or F arrow on the top, but we use this way. But anyhow, so for example, vector field is written like this, f of xy. So input is a pair of numbers, and the output is a vector. So for example, let me write this example, J. Or if you prefer the bracket notation, like this. Then this is an example of a vector field. Then F is a vector field. But in particular, in this case, it's from R2 to R2. Input is R2 and output is R2. So we say vector field on R2. So for example, for this case, for each input, let's say 1, 0, we get as an output 0, 1. Or if your input is -5, 1, the output is -1, -5, etc. So, and then now, how are we gonna interpret this more geometrically? So here's a geometric interpretation. For example, let's use this example. F of xy. So for each input xy, the output is -y x. All right. Then, So that means it's a little difficult, but here's the thing. So the input is R2, so the input space is xy plane. And then for each point on the xy plane, for example, 1, 0, maybe somewhere here, this vector field produces a vector, which is in this case is 0, 1. So 0, 1 is like this. So at 1, 0, its output is vector like this. And if you look at, so this is 1, 0, and if you look at 2, 0, then what's the output? The output is 0, 2. So it's a vector twice longer, but going vertically like this. This is a vector 0, 2. And then if you look at the 3, 0, its output is negative 0, 3, but that's 0, 3. But the vector 0, 3 is a vector going like this way. And so if you go this way, it looks like this. Okay, or here, if you have 0, 1 for your input, for each input, the output is negative 1, 0. So vector negative 1, 0 is a vector like this. And if you pick up this point, 0, 2, the corresponding output is a vector like this. And if you look at here, its output as a vector looks like this, looks like this. And indeed, if you look at here, that's negative 1, 0. Negative 1, 0 gives you 0, negative 1. And this point produces this vector and so on and so forth. And then here you will see this, something like this. And in fact, if you plot a vector for each point, plot the output vector at each point, what you see is more, if you plot a bunch of points, actually bunch of vectors. So for each point, we have the corresponding vector, and if you plot all those, what you see is like this. At each point, you see a vector like this. It's like a vortex indeed, rotating around the origin. And as you get further away from the origin, the arrow gets longer and longer and longer, like this, and so on, like this. Okay. So in general, given the vector field, on R2, so that looks like f of xy, and then that gives you a vector in R2, but each component is a function of x and y. So we have f of xy and g of xy. And those are called component functions. And it looks like this. So on the xy plane, at each point on the xy plane, you get the vector produced by this rule, according to this rule. So at each point, we get a vector. For each xy, we get the corresponding vector like this, like this, like this, maybe like this. So at each point, we get the corresponding output vector, depending on how those functions are. Okay, And then, so in this sense, what you see here is some kind of flow on xy plane. Or it's essentially just a field of vectors. Field of vectors. So the way to interpret this as a flow is this. Suppose xy plane is a surface of some swimming pool. Okay, suppose xy plane is the surface of a swimming pool, and the water is moving around. Xy, and this is the surface of water, swimming pool. And the water is moving, flowing, let's say in this way, flowing like this on the swimming pool, on the surface of the swimming pool. So that means that at each point, we get the corresponding velocity of the water. At each point, you get the velocity. Velocity is a vector. And that is an example of a vector field in physics. So that's why we use the word flow. Okay. Or if you think about it's a field, just think about the cone field. Okay, suppose xy plane is a cone field. You are viewing every cone field from the sky, and then at each point you have a cone. Okay, and then if wind blows, each cone actually, how should this moves or like goes like this way, right? And that gives you some kind of a flow of the wind, flow of the air, and that's one way to think about the word field. All right. Anyhow, so vector field has lots of like physical meanings, and but indeed, this is not really the first time to see an example of vector field. We have already seen an example of vector field in this course. What is that? Well, that is actually the gradient. And indeed, the gradient field. So let's remember this. Given f of xy we have seen the concept of gradient of f of xy. What was this? This is a vector where each component is a corresponding partial derivative. So you take partial derivative with respect to x and partial derivative with respect to y. And then this is an example of vector field, and indeed it's called gradient field. Gradient, but gradient, to be precise, it's gradient field of f. Right? So input is xy, and the output is a vector in R2. So it's an example of vector field, and it's called gradient field. All right. So strictly speaking, this is not the first time for us to see the concept of vector field. Now, we can generalize the concept of vector field in R3. Vector field on R3. For example, let f be. So in order for a vector field to be on R3, we need R3 as an input, and output is also R3. So R3 to R3, from R3 to R3. So let f be the vector field where f of xyz is, let's say, zk. What is this? This means ij component is 0, xy component is 0. So 0, 0, z. So certainly it's an example of vector field. It's simple. Then now, can you visualize this? Well, technically, in principle, we could do that. And the way to think about it is the same as the case of R2. But here, since input is R3, we have XYZ plane for our input. So for each point on the XYZ space here, we have the corresponding output. But output is just 00z. Vector 00z is like vector pointing upward vertically. There's no x component, y component. So just a vector pointing upward. And depending on the height. So that means if you are on z is equal to 0, namely if you are on the ground floor, the height elevation is 0, z is 0. So that means on the xy plane, the vector is 0 vector. So that means if you are here, it's just 0 vector, 0 vector, 0 vector, 0 vector, and so on and so forth. You have just 0 vector. 0 vector is essentially a point. Then now, if you move up by 1 unit up, then the vector has length 1. And similarly here. And if you move up 2 units up, you get the vector twice longer. And if you move up 3 units, you get even longer vector. So as you move up, the vector gets longer and longer and longer. And the same here. Like this. So, and then okay. And if you go into the negative direction, if you go below the xy plane, it's negative, so it's pointing downwards. And then as you move downwards, the length of the arrow gets longer and longer and longer. Like this. So if you think of XYZ space as like inside a swimming pool, okay? So you are inside the water, in the ocean or in the swimming pool, whatever, you are inside the swimming pool. And then on the XY plane, there is no flow. Flow is 0. Water is not flowing. And if you move a little bit up the XY plane, the water is flowing upwards. And if you move farther away from the XY plane, the water moves faster and faster. And if you are faster up in this direction. And if you are below the XY plane, the water starts to flow the other direction. And if you get deeper and deeper, the water flows faster and faster. So that's the meaning of this. Anyhow, so that's the concept of vector field. And then for the rest of the semester, rest of the course, we're going to play with vector field a lot. And for this section, this is all I have to say about vector field.